Welcome to AI Paper Slop. Today we are looking at a brand new paper out of CMU and Salesforce AI research called PACE-E, a proxy for Agentic Capability Evaluation.
Which is a really critical paper for anyone building agents right now.
Yeah, exactly. Because if you're an ML engineer, you know that evaluating LLM agents on benchmarks like SWE-Bench and GAIA is just an absolute nightmare. I mean, it costs thousands of dollars and takes days to run.
The researchers here basically solve this with PACE.
Right. So PACE uses a candidate pool of cheap, non-agentic static benchmarks, things like MMLU or human eval, to predict that really expensive agentic performance.
Yeah, they use SVD leverage scores and Spearman rank correlation to select an optimal proxy subset of just 100 static instances.
Exactly. And then by using this noise-aware bootstrap regression, PACE predicts agentic scores on held-out models with under 4% mean absolute error and an 85% pairwise model ranking accuracy.
And doing it all at 100 times less cost than random target sampling.
Which is just incredible. So our mission today is to unpack exactly how the researchers built this proxy and, what it reveals about how LLMs actually solve agentic tasks.
Yeah, it's a fascinating look under the hood.
So to appreciate why PACE is necessary, we first need to establish exactly why evaluating modern AI systems has become such a massive bottleneck for, you and your engineering teams.
Right, because the paradigm we all grew up with in ML was built on standard static benchmarks.
Standard instruction following, basic math, that kind of thing.
Exactly. They're cheap, they're single turn, and fast. You test a model, it gives an answer, you score it.
Let me use an analogy here. Non-agentic evaluations are kind of like a written multiple choice driving test. They're fast, cheap, but
they don't mean you can actually drive.
Right. But agentic benchmarks like SWE-Bench or Web Arena, they require long horizons, multi-step planning, tool use, and error recovery. So that's like tossing a driver into an actual obstacle course with a real car.
And there's a very high risk of them crashing into a wall.
Totally. So running a single model through a single agent harness can cost thousands of dollars in API fees.
Oh, easily. And it takes days of complex infrastructure setup. I mean, you're dealing with isolated sandboxes, headless browsers, massive repositories.
It's terrible. So the question is, okay, let's unpack this. Can we really trust the written test to perfectly predict who survives the obstacle course?
Well, what's fascinating here is that while agentic tasks feel fundamentally different, they actually rely on underlying atomic capabilities.
Like basic code generation and reasoning.
Exactly. Information retrieval, logic, those are already measured by those cheap static benchmarks.
So the DNA is the same.
Right. The challenge isn't that they are totally unrelated. It's just figuring out which specific static questions actually correlate with agentic success.
Right. Decoupling the selection from the regression. Because if agentic success depends on standard capabilities, how do we find the right questions?
So they built a massive candidate pool consisting of 19 non-agentic benchmarks.
Which covers, 11 different capabilities?
Yeah, coding, multimodal understanding, reasoning, you name it. And PACE needs to select a strict budget of instances, which they set at C equals 100.
Okay, so here's my technical pushback as an ML engineer. Why go through all this trouble?
What do you mean?
Well, why not just throw all the data into a standard lasso or ridge regression, L1 or L2 regularization, and just let the math select the features for us?
I see. Well, the issue there is that there are very few calibration models.
Right, because the agentic tests are so expensive to run in the first place.
Exactly. There were only 14 calibration models in this study, but you have thousands of candidate instances. So standard lasso and ridge overfit catastrophically.
Wow, okay.
Yeah, the paper actually shows lasso achieved 99% accuracy in sample, but it failed miserably out of sample. The Spearman dropped all the way to 0.46.
Oh, that's awful. It essentially just memorized the 14 models.
Right. Decoupling the feature selection from the regression is the secret sauce here. They use a hybrid approach combining a local and a global selection.
Okay, break that down for me. Local selection is target relevance using Spearman rank correlation, right?
Yes. Basically, how well does this one instance's score track with the target agentic benchmark score across all the models?
But if you just do that, couldn't you just end up with 100 variations of the exact same Python for loop question?
Exactly, because for loops correlate with coding ability. But you'd miss everything else, which is why they need the global selection.
The geometric importance.
Right. They run a thin singular value decomposition, or SVD, on the source score matrix to find the leverage score of the instances.
And then they multiply it by the target relevance from the local selection.
Yes. This ensures they capture the global latent structure, not just narrow relevance. You get the best, most mathematically diverse set of 100 questions.
That is so clever. Okay, so once PACE has selected its 100 optimal proxy instances, it needs to translate those static scores into an actual predicted agentic score.
Right, they have two goals for the regression. Goal A is performance prediction,
Which uses linear least squares regression to predict the exact score on the agentic benchmark, right?
Yeah, the absolute score. And the goal B is pairwise preference. They use a structured Bradley-Terry model, which is a logistic regression, to predict which of two models will win head-to-head.
Which is super crucial for ELO ratings and leaderboards.
Totally. But they run into the noise problem.
Right, because agentic benchmarks only have a few hundred instances, meaning the ground truth scores are just inherently noisy.
Exactly. If a model gets a 20%, did it actually earn that, or did it just get lucky on a few questions? If you just fit a regression to this, it overestimates its confidence.
So how do they fix it?
The solution is noise-aware bootstrap regression.
Okay, so what does this all mean for the data? Like, does bootstrapping actually fix the fact that we're essentially fitting a line to only 14 data points?
It does. They use bootstrap resampling over the target instances to stabilize the regression weights against the label noise.
By, like, repeatedly sampling the scores with replacement?
Yeah, you essentially create a distribution of possible ground truths. And if you look at the ablation study, which is table 3 in the paper, removing bootstrapping hurts performance across the board.
Wow.
By averaging over the sampling distribution, the bootstrap improves mean absolute error by 0.77% and Spearman correlation by 0.15.
Okay, so the math is sound. But the true test for AI researchers is whether this actually holds up on unseen models, right? During leave one out cross-validation.
And it does. The results are phenomenal. PACE achieves under 4% MAE and over 0.80 Spearman correlation for absolute scores.
That's incredibly tight. And for the pairwise preference.
It predicts the winning model with roughly 85% accuracy.
And crucially, at equal prediction quality, PACE is 100 times cheaper than a random sampling of the actual target agentic benchmark.
It's a game changer for ML budgets for sure.
But here's where it gets really interesting to me. If 100 proxy instances are great, wouldn't 500 be even better? Where's the point of diminishing returns?
You'd think so, right? But if you look at the budget sweep in the paper, with just C equals 25, the model already gets about 84% pairwise accuracy.
Wait, really? Just 25 static questions can predict an agentic coding task with 84% accuracy?
Yeah. C equals 100 is just the practical sweet spot for stability. If you push it to C equals 500, the absolute score prediction actually gets worse.
Wait, worse? Why?
The MAE rises to 3.44% from an optimal 3.30% at C equals 400.
Oh, because the small calibration set starts to overfit again.
Exactly. You start pulling in weaker and weaker questions, which just adds noise. The pairwise ranking continues to slightly improve, but the absolute score degrades.
That is fascinating. You know, PACE wasn't just designed to save money, though. By looking at exactly which 100 instances the algorithm selects, ML engineers get this unintended bonus.
Which is?
It acts like a DNA sequencer for benchmarks. Instead of humans guessing what SWE-Bench measures, PACE mathematically extracts its capability signature.
Oh, right. And every benchmark naturally selected instruction following and reasoning instances.
Obviously, those are the table stakes. But the rest of the splits were highly revealing.
Take GAIA, for example. It heavily relies on instruction following, specifically ifeval and verification.
Which makes total sense for a browser QA task with really strict formatting constraints, right?
Totally. But SWE-Bench verified was dominated by multimodal understanding and information retrieval.
Which is so wild. I mean, even though it's a text-only coding task, the proxy mathematically selects visual benchmark instances to predict its scores.
Right, because those complex visual tasks are just the best at separating the frontier models. Standard coding tests are too easy for GPT-4 now.
And what about SWT-Bench?
That one spikes on planning and verification since models have to write tests to trigger specific bug paths.
So if we connect this to the bigger picture, developers can actually use this as a diagnostic tool.
Absolutely. You don't just get a cheap proxy, you get interpretable feedback on exactly which sub-skills your model is failing at when it completely bombs an agentic benchmark.
It's brilliant. PACE essentially allows developers to cheaply rank candidate models and monitor training checkpoints with dense feedback, long before ever spending money on a full agent harness.
Though there are a couple of limitations we should probably mention.
Right, like if a new model is wildly out of distribution.
Yeah, if it has a totally weird architecture, the proxy might break down. And also, If developers game the known proxy set,
Benchmark contamination.
exactly, if you train on the 100 proxy instances, the correlation with the real agentic benchmark will just collapse.
Goodhart's law strikes again. When a measure becomes a target, it ceases to be a good measure.
Exactly.
So to tie this all together, I want to leave you with a final kind of philosophical question to ponder. If a model's complex, multi-step, quote-unquote, agentic behavior can be accurately predicted by a simple linear combination of static multiple-choice tests,
Does agentic capability actually exist?
right, does it exist as a unique, emergent phenomenon, or is it just an illusion created by stacking basic skills on top of each other?
It's a trippy thought.
Something to mull over until the next episode of AI Paper Slop.